All right, we now got to 3.2, and I hope you'll find that this section is easier, although there are a lot more questions in your homework. But once you get the central two ideas, really a lot of the homework flies by. But we got to learn a few things here, so let's talk about it. We're moving on from just quadratics to any degree, and you can see I've put some crazy examples here. Do not freak out. Once you see end behavior, you'll see why. I was kind of trying to, I don't know, joke with you or just show you what this is. But end behavior for any polynomial means what does the polynomial do as it continues to move left forever? And what does it do as it continues to move right forever? That's what we mean by end behavior. So, in other words, like this graph goes up into the left and this graph goes up into the right, or we would say it as it goes left it rises, and as it goes right it rises. Now this graph, as it goes left it falls, as it goes right it falls. This graph, as it goes left it rises, as it goes right it rises. And what you'll notice is that for quadratics, well, you always say the same answer, and we're about to find out the reason why. So if you've got a polynomial, we could just write that. At some point, you've got a highest degree term. So this is a polynomial that, by the way, we would say has degree n. It means it's the highest exponent in the problem, and that's referred to as the degree. And the degree, well, clearly we're saying, has some impact on how this graph is shaped or what it does. Also, that number out front, has to do with something about its shape and what it does. So in other words, what I'm telling you is, I know the shape of these graphs up above because I can see what my highest exponent will be. It'll be squared. And I can see that there are three different values of a that all shaped this graph in some way. Namely, the negative flipped it downward, and positives kept it going upward. Interesting. So from this highest degree term, and knowing now what degree means, it's the highest exponent in a polynomial. So maybe you could look at these two and figure out which one it is. Careful, they might trick you and switch the order, and you might need to reorder it, but I've written them in order for you, so I kind of gave away the answer there. But now from there, we get a chart. And we'll say this. There's two options: when n is even, when n is odd, and when a is positive, and when a is negative. Those are your four options. Now, from those four options, I'm going to very crudely, so to speak, write your end behaviors. If a is positive and n is even, then your end behavior is up and to the left, up and to the right, or rising to the left and rising to the right. But when I used to do this, I would say up and down, but again, rising, falling. So actually, we just answered the question right here. Why do quadratics normally open up? Because quadratics have an even exponent, and usually the number out front is positive. Great, we just solved the mystery of why these graphs have their shape. Up next, let's keep things positive while we can. If something's positive and n is odd, then here we go. Anything positive and odd, well, let's talk about being positive. If you're positive, you will end by going up and to the right. But if you're odd, you will have disagreement between the two. So again, this is a very shorthand way of saying this graph will go down to the left and will go up to the right. Or again, it will fall as it goes left and it will rise as it goes right. So, what did we learn so far? If you're positive, you will end by moving up and to the right. Think about a stock chart if you've ever looked at those. If things are good and companies are making more money, or they're having, rather, I don't want to say making more money, to be technical, when they're evaluated as having more worth, then it goes up and to the right. But if something's even, then they match. And hey, guess what? How many of them match? Two. What's even? Two. And if it's odd, one of them will kind of do that stock phrasing, and 1 will go the other way. 1 and 1. Hey, guess what? 1 is an odd number. So 1 of each, even, both do the same. So with that being said, you probably know what's going to happen down here. What if you're negative? If I'm negative, then I will fall as I go to the right, or I'll move down. And if I'm even, I will match what I saw before. And finally, if I'm negative, I will end by going down and to the right. And if I'm odd, then this one will move down and the opposite will move up. So there we go. There's a lot of memorizing to do here with this basic chart. Hopefully I gave you some explanations. Positive always ends by going up and to the right. Even matches, odd flips. Negative always ends by moving down and to the right. Even matches, odd flips. And so, just to point this out to you, as a really, really basic example, if I had, y equals 2x minus 7, this is just a basic good old-fashioned line, and it's been a while since we've seen those, but that has a y-intercept down here at negative 7, and a slope of 2, which looks essentially like this. And guess what? There's your highest degree term. It is positive because the 2 is positive. Careful, the 2 isn't telling you if it's even or odd. The 2 is telling you if it's positive or negative. And what's the exponent on x? Technically, invisibly, it's 1. And so this is positive odd, which means it falls into, let's see here, the positive odd section. Down to the left, up to the right. Hey, look, there it is. This chart is not lying to you. So with that being said, take a minute or two. You could probably pause the video. I'll wait 30 seconds, but now you hopefully see the silliness of writing down this crazy example. The only thing that determines end behavior are or is the first and high, or rather should be first, but the highest degree term. Go ahead and look at the end behavior for both of these. Think about it a little more. And let's see how we did. Well, this graph is positive and even because 5 is a positive number and the 4, the exponent, is an even number. And so because of that, anything positive ends up, we'll follow the homework's wording, rising to the right. And if it's even, it will match, so it also rises to the left. Or in other words, as I would have written it, up and up to the left, up to the right. Interesting. All right, this one. What's going on with this example? Well, it's negative 8,074, which is a big number, but guess what? The only thing that matters is that it was negative. From there, what's my highest exponent? Well, that's why I grabbed that number, because 31 is my highest exponent, and 31 is odd. And so from there, anything negative ends by falling to the right or down to the right. Anything odd has 1 and 1. So if it fell to the right, then it will rise to the left, as your homework will say it. So again, hopefully you see the silliness of this example. That giant number doesn't even matter. This giant number doesn't even matter. Only the highest degree exponent matters. And even so, this negative 8,074, all I'm pulling out of it is that that number is negative. The exponent is when I care if it's even or odd. And even so, it's not hard to see whether a number's even or odd, no matter how many digits it is, because it's only the last one that matters for determining even or odd. So hopefully that kind of made you laugh and hopefully put you at ease that this is a fairly simple concept once you memorize this chart. Okay, from there, there's other main things we care about polynomials, which are their roots. Now, we just spent a lot of time looking at those roots because roots, by the way, is another way of saying x-intercepts. So when we had quadratics, we could either find them by factoring directly, by observing its graph and hoping that it crossed evenly, which it did, or again, don't miss this, expanding this out and getting it into this form and factoring that. We just didn't do that together. Or finding something that could not be factored based on the sentence. There are no factors of 6 that add to 14, but there is a quadratic formula that always solves any quadratic, and we can get our answer there. Now that's what we do with quadratics. What do we do with higher degree polynomials? How do we find where they cross the x-axis? So remember, roots, maybe what I'm saying first, is x-intercepts. Two words for the same thing. Why? Because if you invent something, you can tell people how to memorize it in how many different ways. But for us, what we're now looking at is, we'll say it's best observed by factoring. And then, here's a new word. Multiplicity is how many times, parentheses, exponent, the root occurred. I'm running out of space. I got to write one more thing. And in fact, we'll write it up top here. Once again, even and odd means something. Even, let's see here. Will, I forget the way the book phrased it. Let me pull it up just so it's easier for us. All right. So for even, what the way your book phrases it is it turns around. I used to refer to it as bouncing off. And odd, I used to refer to as passes through, but we'll say crosses. Now, specifically, crosses the x-axis or turns around at the x-axis. So we won't concern ourselves too much with the nuts and bolts of what that means. We'll save that for the next examples. But for now, we get to go through these pretty quickly. So roots are x-intercepts. They're best observed by factoring. And hey, take a look. The first examples, A and B here, are already all factored out for us. And so we need to determine the roots and their multiplicities and kind of talk about what they do. Well, again, hopefully you're looking at these and thinking, that doesn't sound too bad. Because look, to make this 0, or since this is factored, if I flip that number around, that's 3. Now careful, 3 occurred more than once because it had a squared on it. So we'll say it's 3 multiplicity 2. And then we'll say my other root is -4. Now, in other words, on your homework, it's going to say, what are the roots? And your answer is going to be 3 and -4 only. The next box is going to say which root occurred twice and which root occurred once, and they're going to be kind of multiple choiced out. But you would say 3 occurred twice or an even amount of times, -4 occurred an odd amount of times or once, depending on how it says it. And so what we're then going to say is the graph turns around at 3 and crosses at -4. Now that's the only time I'm going to write it out here in person, but that's what we're saying is because this was an even multiplicity, because that exponent was 2, it's going to turn around at 3. And because it was an exponent of 1 at -4, then it will cross at -4. We'll see what that means on the graph, but that's all we are identifying for now. Let's look at the next one. This one should go by again pretty quick. My roots are, and I'm even just going to do this and write it like this, -2, multiplicity 5. So hopefully you now know whether -2 is going to turn around or cross. And guess what? It's odd amount, so it's going to cross. There's also, I guess I'll write it like comma separated. There's also 3, and that's multiplicity 4. Again, as I pull them out of the parentheses, the signs flip just like in vertex form. And then there's also -18, which is only a root once, or I guess multiplicity 1, but we don't usually write that when we say it. So, hey, guess what? These two are going to cross, because that was odd multiplicities. this one is going to turn around. So there we go. Those are our three uh, roots, multiplicity, and graph behaviors. Now I stated the graph behaviors, but that's what you would write for each one of them. Now we get to this last one, which unfortunately is not factored out for us. And the short answer is we're not going to be able to determine these roots at all unless we do factor it out. So here we go. Thankfully, each one of these terms shares something. They all have at least one power of x, so I can factor that out. And I hate to be this person, but this is that point in the semester where I say, remember in Module 1 when you had that quadratics review? This is why that's super important, and it's all coming back to haunt us now. So if you didn't take my advice and really, really master that section, it might be a good idea to go back and just look at those problems really, hopefully quickly, to catch up on them, and then come back to this section because it does feel overwhelming to say, I thought I was getting the concept and now I had to do this again. Now I feel like I don't know the concept. Be careful of that. You might know what's going on now in this new module, in Module 3. You know how to decipher all this information, but now you forgot how to factor, and so you can't do the easy part. You're stuck on what should have been easy earlier, and now it's hard again. So just keep that in mind. It might be worth going back and reviewing that review section. Okay, anyways, we got a factor, and so are there factors of 49 that add to 14? There sure are. There's 7 and 7. And not only that, but in order to make positive 49 and add to 14 and have that 14 be negative, each of these have to be negative. That's how they add to or combine to a negative 14, but multiply to a positive 49. Which means, though, that this shouldn't be the final way I write my answer. I should write it like this. Okay, so from there, to close this out, what are my x-intercepts? My x-intercepts are 0 with a multiplicity of 1, because plugging in 0 to just a simple x with nothing else would make the whole thing 0. My other root would be 7, because it's the opposite sign, and it would be, whoops, multiplicity 2, which means it would turn around at 7. All right. That does it for those questions. We've got two more, and we're going to do everything here. We're going to talk about the end behavior, we're going to talk about the roots, and we're going to form a basic sketch of the graph. All right, for the first one, we can easily determine the end behavior because it's the highest degree term. There it is. Now, what is this highest degree term? The number out front is positive. So first we'll talk about, maybe we'll write it, end behavior. Well, we had a positive, whoops, even function. So that means our end behavior is up and up, or rising to the left and rising to the right, because anything positive ends by moving up or rising to the right. Anything even matches what you said at first for the left-hand side. Okay, so whatever the ends of this polynomial is, it might cross through or bounce off some roots, but at the end of that, we know it's going to go up and to the left and up and to the right at the ends of those roots that we find. Well, now we've got to find the roots, and once again, this is not factored, so we got to factor it. There's a shared x squared in all three of those, which would leave you with, as you factor it out, this. From there, we're not done yet because we got to see if this can be broken down. Are there factors of 1 that add to 2? There sure are. 1 and 1. How do we add to 2 but have a negative and a positive at the end? Well, we saw that before. They're both negative. And so now, whoops, sorry, that was x squared. So now, how do I write this? Well, it's actually x squared and then x minus 1 squared. And so now I know my roots. My roots are 0, multiplicity 2, and 1. multiplicity 2. And in other words, I now know that at my roots 0, because that's what I plug in to get 0 for the whole thing, and 1, I know that my graph is going to turn around at those endpoints. Now, the last thing we need to do, we've talked about the end behavior, we found the roots, we want to sketch a graph of this. Now, this graph is not even going to have any labels or axes on it, but we know we're doing something at 0. We know we're doing something at 1. I'm just going to give myself enough space to do it. And from there, I know my end behavior from my roots. The furthest left root, what am I going to do after that? I'm going to go up and to the left after my furthest left root. I'm going to go up and to the right. So now we're finally seeing what that end behavior was talking about. What do you do after you've encountered your leftmost root? You continue to go up. What do you do after your most or rightmost root? You continue to move up. Now from there, my roots had even multiplicities, so are they going to cross through this x-axis? No, they're going to turn around. So what does that mean? It means around this root, instead of crossing, I will turn around and look like this. And what will I do here? I will turn around and do something like this. And what happens? At some point, these are going to meet, just trust me, and they will always end up meeting smoothly. So this is the sketch of your graph. Once again, how did we do that so quick? Well, I found my roots, 0 and 1. I looked at my end behavior and said, from my leftmost root, I will continue to go up. From my rightmost root, I will continue to go up. At my left and rightmost root, because there were only 2 of them, I will bounce off, or again, turn around at that root. So if I was ending by going up and to the left, I'm going to bounce off and now go up right after that root as well. This one bounced off as well, and they'll always meet nicely and smoothly. If you had the question, is it possible for like me to graph my end behavior and say that this one passes through and then this one bounces off? How do they connect through the middle? The answer is that would never happen. If that's what you got, then something in your intermediate results was wrong. So they'll always be a nice way to connect them. And by all means, you could plug this into a graphing calculator and see that. All right, let's go through this last one. Um, Now this one's a little bit trickier because what is the highest degree term? Well, I don't know yet because I haven't distributed this whole thing out. But remember, it's only the highest degree term, so I want you to think about what would it look like to have x minus 3 multiplied to itself 3 times. I don't know what that would be entirely, but I know it would start with x cubed because that's what I would get from multiplying each one of those out if I FOILed it. And then if I had x cubed and I multiplied this x plus 3 here, I know I would then at least have my highest degree term being x to the 4th. And then wait a minute, there's also an x out front. So I already know that I don't need to do any work to know that this is going to lead with x to the 5th, blah, 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 blah. If you don't believe me, then I don't want to say FOIL it out, but try it. From there, this is positive and it's odd. So I know what my end behavior is. I'm not going to write positive odd. I'm just going to write what that's going to do for me in behavior. My end behavior, because it's positive, will end by going up and to the right. Because it's odd, it will go down to the left. From there, what are my roots? My roots are x equals 0, technically multiplicity 1, x equals 3, multiplicity 3, and x equals negative 3, once again multiplicity 1. So can we sketch a basic graph of this? Yes, we can. I'm going to do something at 0, I'm going to do something at positive 3, and I'm going to do something at negative 3. Okay, those are my 3 roots. Now what comes next? The end behavior. From my leftmost root, I'll move down. From my rightmost root, I'll move up. And now, careful, the roots, I guess we should have written them in, what's the word, numerical order, but we are more so writing them in order of how they appeared in the problem. But negative 3 happens first. Now, negative 3 only was a root once, odd degree, And so it's going to pass through. And then it's going to start curving around back towards 0. And 0 is also a root once, and so it also passes through. And then, this is where things get interesting. 3 is a root 3 times, so what does it do? It does pass through, but if you've looked at cubic graphs, you know that they start to get a little bit of a wiggle in them when you graph a cubic. And if you don't remember, go back and look at your parent function for x cubed. You'll see it has just a little wiggle in it. And that's all there is to this section. And what I would highly encourage is well, actually, here, I'll do it for you. I know we've gone a little over this time. But I wanted to show you, I plugged these into Desmos. Now you'll have to mess with the scaling, but you can see clearly that our graph was totally correct. Again, our scaling was off, like, the way we drew that middle section was a little bit more extreme. But really it's not, because we could have just decided that we were really, really zoomed in here. Like maybe our y-axis was going from negative zero point 0.2 to positive zero point 0.3. And look, now it's scaled accordingly. So really what we're doing when we draw these graphs is we're just caring about, hey, there's my x-intercept, there's my x-intercept, I did my end behavior, and at some point they have to connect. Because they both bounced off, they made this kind of little hill here. The other one, because it's cubed, it's going to look a lot crazier. I need to definitely adjust my scaling now. So because it's cubed, I just kind of, with time and practice, know I should probably look at this from negative 200 to 200. And once again, you can now see pretty much what we graphed, although mine was a little bit uh, different looking here, but it passed through negative 3, eventually turned around, passed through 0, turned around, and then squiggled through positive 3. There's that cubic shape that, again, like, if there was none of this other stuff, here's what I mean by cubic shape. There's that classic cubic shape, but because it's wrapped up in this other bigger polynomial, it kind of got stretched and warped. But that's a huge concept. Thank you for the extra time on this video. I know our last one went a little short. Anyways, I'll see you on the next one.